Hi. Today I have the pleasure of introducing to you Nanongkai, who will be giving us a talk on negative weight single source shortest paths in nearly the theory of
Uh,
CIs. He is also one of the most well-traveled researchers in academia. In fact, after childhood in Asia, in Thailand, he moved to Georgia Tech for his PhD, which he completed in 2011. He later moved to Vienna for his postdoctoral studies. He has also worked at Nanyang at Singapore and Brown University. He was later an assistant professor at the University of Vienna in Austria, and then a professor at University of Copenhagen in Denmark. Currently, he is the scientific director in the Algorithms and Complexity Department at Max Planck Institute for Informatics at Saarbrücken in Germany. He has been well awarded also along the course of his work. Recently, earlier he was awarded the Doctoral Dissertation Award in 2013, and in 2016 he was awarded the ERC Starting Grant. So his research interests in generally on graph algorithms and complexity, and his current focus is on sequential, distributed, and dynamic graph algorithms. Most recently, he won the Best Paper Award at FOCS 2022 for the current paper that he is speaking to us about today. So without further ado, I would like to hand it over to Danupon for his much-awaited talk. Over to you, Danupon.
Thank you so much, Rahul, for the very nice introduction. And it's great to be back virtually to India, at least, hopefully physically at some point too. So yes, I will talk about negative weight shortest path today. And by the way, I guess Rahul forgot to mention KTH. So I am at KTH for quite some time, and I'm still affiliated with KTH right now. So I should mention this here. Yes, it's a very nice place in Sweden. In any case, so I'm going to talk about this work now, which is a joint work with Aaron Bernstein from Rutgers and Christian Wolf Nielsen from University of Copenhagen. And please feel free to ask me questions at any time. I love questions. So first of all, let me note that some notations and algorithms that you see here might look a bit different from the paper that we have on arXiv right now, but the new version that might be more consistent with the talk today is going to be out very soon. In any case, it's pretty much the same ideas. I just changed something so that it's easier to discuss in this talk. All right. So let me start by defining single source shortest path, although I hope everyone know what it is. So we are given directed weighted graph, and W will denote the weight and a source vertex S. And for today, I would assume that the weights are integers. Okay, this sometimes can be removed, but in this talk, it's important. And the output that we want is a distance from from S to every vertex V, or even the shortest path. For example, this is your input graph. And this is the distance from S to A is -2, and from S to D is 1, because you can go from S to A to D, right? And you can also draw the shortest path tree that look like this, the blue thing here. So some notation that I will use throughout. M will be the number of edges, N number of vertices, and W will be the most negative weight. So I will assume that WE, the weight of every edge, is at least minus W, okay? And the distance will be just denote the length of the shortest path from any node U to any node V. And I will hide polylog in most of the time of this talk, which with the notation tilde O over here. All right, so now I hope you have heard of shortest path and at least these two textbook algorithms. Dijkstra algorithm, we all know that it works in near linear time, in particular m plus n log n. And the problem is that it only works if you have non-negative edge weights. This is some basic thing we learned. And so we also learn that Bell-Manford, on the other hand, can handle negative weights. But the problem is that it takes much longer time, or mn time, so it's not near linear. And the question that has been studied for quite a few decades is, can we have a fast algorithm for negative weight shortest path? Maybe something as fast as Dijkstra? but also work for negative weight. So here's a brief history of the problem. So in the early 50s, the classic work was already done. For example, Bell-Manford was known at the time, although this was due to other people, Chimbell and Moore. So sometimes this is called Chimbell, Bell-Manford, or Bell-Manford Moore. And in around 80s and 90s, questions, yes. Did somebody ask question? No?
No, I don't think so. Please go
All
ahead.
right. Okay. So in the 80s and 90s, some development happened because of scaling techniques. So the algorithm that we know of takes time, m root n log w. And meanwhile, there are some special cases solved. One of them is the breakthrough by Factorenput and Rao that get near linear time for planar graph. And also, people also know faster algorithm for bounded genus graph and minor free graph, for example. And in recent years, in the last 5 years, we have seen a lot of uh, interesting, exciting results based on continuous optimization and also dynamic algorithms. And the best we know of for this problem is m to the 4/3 roughly, and m plus n to the 1.5, which means that for dense graph, we already have near linear time, and for sparse graph, it's m to the 4/3. Okay, so this is where we stand right now until 2021. So now in this work, in this talk, I will talk about our result that is a randomized, and in particular Las Vegas algorithm that takes time m to the log to the x, log w time in the expectation. And let me note that we didn't try to optimize this log to the x term. So you probably see something better soon. And also, what does our algorithm do? It returns either a shortest path 3, or it reports a negative weight cycle, because negative weight cycle will make everything infinite, in at least anything that can be reached from the negative weight cycle. This is also what Bell-Manford does. So our output is pretty much similar to a Bell-Manford. And maybe one highlight of the techniques for now is the tool called low diameter decomposition. So basically, if I can go back maybe 20 years ago, I hope if I just shout out, low diameter decomposition, then somebody will already know how to approach this problem. So we don't really need anything new in the last 20 years, just this low diameter decomposition, which was an old tool by itself. I'm coming back to this in a few minutes. So let me end this part by talking about an independent work by Chen, King, Liu, Peng, Prof, Gutenberg, and Sakdeva that solve mean cost flow in almost linear time, meaning that they can solve mean cost flow in m to the 1 plus little o1 log w. So it's slightly higher than what we got, but at the same time, it works for a lot of problems. So mean cost flow, negative weight, single source shortest path by part-time matching, and so on. So this is a great breakthrough, definitely. And it can be thought of as culminating this line of work on continuous optimization and dynamic algorithm. So let me note that our approach is quite different. We don't need any of this. We are using combinatorial tools and just low diameter decomposition. And now with our and this result, very great result in mind, let me also mention, where we think we should go next. So again, we have almost linear time algorithm for a lot of fundamental graph problems. So are we done? And I think we're not. For the future, I think we need a few things. First of all, we probably need an algorithm that is simple. And by that, I mean maybe implementable, experimentable, or teachable. And we probably need an algorithm that works across different paradigms. This is one of my research goals, is to have an algorithm that works in other model for computation, for example, communication complexity, distributed algorithm, parallel algorithm, streaming algorithm, dynamic algorithm, and so on. And I think we are still quite far. And hopefully, in this work, we have shed some light, at least for this special case of single source shortest path. So that's what I hope you can check if you agree with this in the end of the talk. So this is probably a good time to ask questions for the first part, if there is any. If not, then let me continue. So for now, the
One
rest.
small
Yes.
question. This is only for directed graphs, is it?
Which one?
Your algorithm, is it for directed?
My algorithm is for directed graph.
Okay.
I guess this is the most general setting of graph, except that we require integral weights. Okay.
So, quick question. So, there's an emphasis on log W, which and like W being the most negative.
Right.
So, I would imagine like if like the max weight also, even if it's positive, shows up. So, like I'm wondering why the
so the max
distinction.
weight will not show up in the log factor at the least. It
Okay,
will show. Yes.
In the bit complexity or the
Right. So you assume that you can you can in one, like you in the usual way that we assume when we analyze algorithm.
Unit time operation.
Okay. Right. Exactly. Yes.
So I mean, the W is interesting because it like makes an appearance in the running time as well.
Exactly. Yes.
Okay. Correct. Thanks.
Thank you.
Hey, W is no beforehand, or would you?
Oh, I mean, you can just read the graph and compute W, right?
Yeah.
All right. Okay. So then let me continue. So for the rest of the talk, first of all, I will talk about the key tools that we need, which is low diameter decomposition, just to define what it is. And before I can explain you the algorithm, I need to tell you one basic, which is a price function, or some of you may know it as dual solution. I was told that, I never taught undergrad course on shortest path before, but I was told that price function is something that people learn after, in undergrad already, but just a quick reminder. And then we will jump to the key high-level ideas. And with these high-level ideas, I will show you a warm-up result, which gives you m root m time. And from there, it's not hard to actually get near linear time that we claim. And if we have time left, I will talk about low diameter decomposition a bit more. So that's the plan. And again, feel free to ask questions. I don't have to finish everything. So, right, low diameter decomposition, what is it? So we have input graph G, and besides that, we have a parameter D. The input graph, we have directed graph, and with non-negative weights, by the way. So here's the important thing. Low diameter decomposition only works for non-negative weights. And also I have some positive integer D. And what I want to output is a set of edges called EREM. REM means remove, okay? So, and I want to have two properties. First of all, if you look at the graph where you remove these EREM edges, then I compute the strongly connected components. I want this strongly connected component to have something that is called weak diameter of big O of D. So what is weak diameter? It just means that for any pair of vertices in the same strongly connected component, the distance between them, so from U to V and from V to U in the original graph G, okay, is big O of D. So this is what it means by weak diameter. And if you look at the picture, what happens is that if I remove EREM, which is the red edges here, I have strongly connected components, which is denoted by this green oval. Then, of course, first of all, there are some edges between strongly connected components, right? But they just only go one way, from up to down. And if you look at two vertices inside the green oval, then the distance between them in the original graph has to be big O of D, from U to V and from V to U. I hope that makes sense. And another property that I want is that an edge, the probability that an edge is in EREM is pretty small. And by small, it means the weight of that edge divided by D roughly. But except that there's some this parameter log square and another small number n to the minus x here, but this is just for technical reason. What is important is WE divided by D. Okay. And I claim that we can compute this low diameter decomposition in tilde of OM time, in near linear time. By the way, let me note also that the probability that an edge is in EREM is not independent. Any question about this description?
So of course, you're
yes.
assuming it's possible. Like if I have a complete graph, like bidirected, then for certain values, like I mean, the trade-off can't be satisfied, right? Like, or
it's actually you can have this for any graph.
okay.
Yes.
Oh, I see. So it's not
Right.
that even that
Yes,
is not obvious.
Yeah, it's not obvious. We have the only way I know how to show this right now is through our algorithm.
Okay.
There's no simple argument to say why this should be there, but that's a good point. Yes. Any other question? So,
and if the does have negative integer weights, then what you
yeah, then you cannot run this algorithm, right? So you have to do something else, and that's one of the things we need to take care of later. That this algorithm only works with positive integer weights, but for say shortest path that we want to solve, it has negative weights too. All right. Any other question?
Hey, so yeah, like just to sort of belabor my point,
Yes.
like what you want is the distance in G to be order D. So like if you have just trying to anchor my understanding, if you have a complete bidirected graph, so every pair of vertices, like there's an edge going both ways. In that case, this would mean that you'd have to remove enough edges to ensure that there is no strongly connected component.
I mean, you can do two things, right? If every edge has small weight anyway, then you can just keep the whole graph, and if the whole graph already has small diameter, right, then you will be fine, right? But yes, otherwise, another option is remove a lot of edges, and that depends on D, right? You can see why D kind of plays a role here.
Okay. And
yes.
so like the way to read order D is it's like some
3D
distances. Yeah. Okay. At most 3D.
Yes, at most 3Ds. Yes.
Okay.
Thank you. All right. So, okay, let me show some examples just to make sure that you understand what is happening for this LDD. So suppose you have an undirected graph, which means that you have this bidirectional edge, right, between every pair. Then this LDD can be computed pretty easily by picking one vertex Vi. So the graph is called V1, V2, and so on. So I pick some random vertex Vi between where I is between 1 and D. And then I remove an edge from Vi to Vi plus 1. And then I skip D vertices and then remove another edge, right? So then you will end up with, connected component with diameter D. And this is actually strong diameter in the sense that they can reach each other within D hops inside the component itself. And every edge will be deleted with probability 1 over D, right? Because I pick I randomly. Another example is if you have a cycle like this, a directed cycle, then what I can do is just pick one edge and remove randomly, and then the SCC will be just the singletons. So in this case, the low diameter is already guaranteed, and also every edge is picked to be in EREM with only probability 1 over n. So it's pretty small. Okay, so just to give you an idea, but of course, this is too simple to work in general, and in general, there is something more to be done. So let me give you an overview of what happened for these LDD algorithms. It's actually a pretty old algorithm. So For undirected case, this has been studied for a long time. One technique that has been used is called ball carving. So the idea is pretty much you pick a vertex and you grow a ball around that vertex with radius r, where r is a geometric random variable that of value roughly log n over d. Okay, and then you keep doing that. So if you look at the picture on the upper right, this is one ball, and then you remove another ball, you remove another ball, and it looks like this now. So, and you, in the end, if you keep doing this, you will get a picture that looks like the cover of this book, for example. And as suggested by this book, this is a technique that pretty well known already. It was used in network synchronization and probabilistic tree embedding, for example. And it works in many settings. So people have studied this technique in distributed setting, parallel setting, and so on. Okay. So for the undirected graph, we can already solve this in near linear time. But for the directed graph, it turns out that this is quite new, but you don't need much more new ideas. So just to give one quick keyword. So the idea is to remove some balls instead of all the balls, first of all, and we will have to recurse on the balls. These are pretty much the only thing you need to modify from the previous algorithm. Unfortunately, I won't have much time to go into the details of this algorithm. And so far, the only known applications of this technique is decremental, single sort shortest path by Bernstein, Wolf-Nielsen, and Probst Gutenberg. And we kind of borrow the idea from this paper and even the previous papers that this paper borrow from to construct our LDD algorithm in near linear time. But we also wrote in our paper that we don't think this is our main contribution because the ideas were already there in the past. Okay, it's more about using this LDD. And let me leave here as an open problem whether there are more applications of this technique because it's pretty new and for now we only know 2 applications, which is decremental SSSP and negative SSSP. And also let me know that you can look at the link on the right side here if you want to learn more about this technique. Any question before I move on to the next step? All right. So now I will talk about price function, which is a basic thing for shortest paths. So, okay, definition, what is the price function? So it's just a mapping from a vertex to some integers. That's it. That's what we call price function. But what does it do? So now I will define something called reduced weight, W phi, for price function phi of an edge UV. And this weight is just the same, the original weight plus phi u minus phi v. Okay. And with these weights, I can define a reduced graph, which is the original graph, but with the weights modified. So for example, here, if I have a weight of -5, if I put price function 0 here and -2 here, then the weights, the reduced weight will be -3, okay? For now, just remember that it is a way to assign some number on the vertices to change the weights of the edges in the graph. And one important lemma here is that shortest path in G and in the reduced graph G phi are the same. So price function doesn't really change shortest path, and that's the cool thing about it. So just a quick proof. So if you look at the weight of a path, right, from X to Y, then you can write it as the original weight plus phi X minus phi Y, because most of other things will cancel out when you compute the weight of this path. And so the order of the length of the path will not change because for every path between X and Y, they will have the same phi X and phi Y. Okay. So this is one takeaway that I hope you will remember. If I keep modifying the graph with the price function, maybe G phi 1, G phi 2, and so on, shortest paths don't change at all. We still have the same shortest path. Another takeaway is that a good price function, which I will define, help you compute distances meaning help you solve shortest path, and vice versa. So what do I mean by this? A good price function, or or you can call it feasible dual solution, is a price function phi such that W phi is at least 0 for every U and V. Okay? So you have non-negative weights everywhere. And it's clear that if you have a good price function, then you are pretty much done, because once you have non-negative waves, then you can just use Dijkstra to compute shortest path. On the other hand, if you can compute shortest path, if you have a fast algorithm, so if you have distances, then you can use it as a good price function. So what do I mean is that if we pick any source S and we set phi V to be the distance between S and V, then I claim that the reduced weights of every edge is at least 0. And it's just follow from this simple calculation, which I hope you can have a look later. So you just replace phi u, phi v by the distance here, right? And you can prove that the distance has to be at least 0. Otherwise, this is not going to be the correct distance. You should be able to improve it. And this is the hint here, because of triangle inequality, basically. But the proof is not important here. The important thing is that you should know that good price function and shortest path and computing shortest path are pretty much the same problem. Another takeaway is that if you have special case where edges inside the strongly connected components are already non-negative, then you can immediately get good price function in linear time. And this is done by an algorithm that we will call fixed DAG edges. And we call this because if you look at the picture, right, you have strongly connected component that you have non-negative weights inside, and then you have these blue edges between strongly connected components. They form a DAG, right? And they might be negative. But the fact that they form a DAG, this is very helpful. So in near linear time, we can do the following. We can return a good price function on edges between the SCC and edges inside the SCC, the weights will remain unchanged. So the algorithm is pretty simple. You set the price function of the, so let's have topological ordering of the strongly connected component. And you set the price function of the second component to be minus L, where L is small enough. And this will make sure that the negative weights will become positive between the first and second component. And then again, if the third component, you make it minus 2L, then again, you can guarantee that the edges between the first and the second to the third component will be non-negative again. Okay, this is I guess you can check this pretty easily from this inequality on the right side. Any question about price function? Or let me conclude again, this is all you need. First, the price function don't change shortest paths. Good price function helps compute distances and vice versa. And we have an algorithm called fixed DAG edges, where the edges inside SCC, if they are non-negative, then we can get a good price function in linear time.
Hi, Danupon.
Yes.
Do you mind just going over the fixed DAG edges just one more time, because it seems
Sure. Yes.
Yeah.
So you mean the algorithm or the statement of the
the algorithm?
The algorithm? Sure. I hope everyone understands the statement. Again, the statement is if inside the SCC are already non-negative, then you can make everything non-negative. Okay. The algorithm is, if you change the price function of one vertex, right? Then if you change it to the negative, like you decrease it, then the edge will have the edge from U to V. If you decrease the price function of V, then the weight of the reduced weight of edges to V will increase. Okay. It might be confusing, but you just have to understand that if you change the price function in one way or another, then the weight will change in one way or another as well. That's the only important thing. And so the idea now is that for this, if I care about an edge from the first component to the second component, right? It might be -1, for example. If I decrease the price function of every vertex in the second component, then this edge, the reduced weight will increase by 1, for example. Okay, so if you increase and the weight inside the SCC will not change because everyone changed their weights in the same way. Okay, so now if you change the price function of the second component enough, to be minus L for some big enough L, then the edge from the first component to the second component here will be non-negative. I can guarantee that. All right, and the same thing for the third component. If I make it small enough, and here it should be minus 2L and minus 2 because I want it to be much smaller than the second component too. Then the edge from the first component again will be non-negative, and also the edge from the second component. And again, this doesn't change anything inside the third component and anything between first and second component.
I see.
Would
I see.
that?
And crucial part is that there's no edges from the forward component to the backward component.
Like, yeah, the crucial part is there are no backward edges, right?
Yes.
It will destroy this algorithm. Yes, and that's why it has the word DAG in here. Okay. All right.
And the non-negativity within the strongly connected is reminiscent of the D bound that you had for the flow diameter decomposition.
We are not there yet.
Okay.
Yes, but yes, I mean, at some point we will try to make, so just to give you a heads up, we try to make edges inside strongly connected component non-negative by using low diameter decomposition. And we are going to be there very soon. Okay. Yes. All right. So now high-level ideas of the algorithm. So let me make some more assumptions here. First of all, I will assume that G contains no negative weight cycle. So our only job now is to find distance between from S to every vertex. Okay, we will not report negative weight because we will assume that there's no negative weight. It's a fun exercise to remove this assumption. It's just, binary search, try to add some weights to every edge and then argue what happened. Another assumption that I will make is that the input graph G has constant max degree. So for now, M and N will be pretty much the same thing. So I will use M and N interchangeably. Okay. How can we assume this? So suppose you have a vertex with, let's say, degree 4 like this, A and B and C and D. You can just replace it by 4 vertices here. And you point from A to here, B to here, and then C and D here. And you can check that it doesn't change the shortest path. Basically, because if you want to go, let's say, from A to V and then to out of A by C, right? You can just go on the right picture from A to V1 and then go to V3 and then get out of V3 by C instead. Okay. So now we have max degree constant. Right. So now with this assumption, now the outer loop of this algorithm is something that we call scale down negative weights. And the idea is this: suppose you start with a graph where the negative weight is at least minus W, right? This is the most negative parameter. And I will try find price function phi 1, phi 2, and so on, such that W of phi 1 will be at least minus W divided by 2. So the most negative is not as negative as before, right? And then I will compute phi 2 that is even better. So the most negative is minus W over 4. So it's less negative than before. And if I keep doing this, at some point I will end up with W phi T, where the most negative is minus 1 over n squared, which means that every edge, it sees at least minus 1 over n squared. It sees almost 0. And from this point, I claim that you can round every negative weight to 0 without changing the shortest path. Just to give you a quick argument why this is the case, if the most negative is 1 over n squared, right? Then you just add 1 over n squared to every edge. And you know that the difference between the shortest path and the next shortest path is at least 1 because we assume integer weights. So adding 1 over n squared to every edge will not change the weight of the shortest path too much. And so the shortest path remains a shortest path. Okay. So this is pretty much the picture again. You have minus W and then you get minus W over 2 and so on until in the end you get 1 over n squared. And from here, we never change, we only modify the graph using price function, which doesn't change shortest path. And in the last step, we add something which I use this notation, add 1 over n squared, something tiny to every edge. And now I have non-negative weights. Any question about this outer loop?
Why not stop at 1 over n and why go till 1 over n squared?
Yeah, I think I'm just trying to be safe. I think you can stop at 1 over 2n or even n plus 1. All right. All right. Okay. So now the key idea now is how to implement this step, getting W over 2, W over 4, and so on. That will be the remaining of the talk. So, and I will just focus on the showcase where suppose I start with an edge of weight -2, all right? So every edge has weight at least -2. And I will come up with a price function phi so that every edge has weight at least at least -1. Okay. So again, we have an input graph where the weight is at least -2, and then I will compute price function so that W phi E is at least -1. And the plan is the following. Now I have to define a few more graphs. And this is very important, by the way. So G plus 0 will be just a graph G plus 0 weight edges from the dummy source. So I'm going to add a dummy source to all nodes. So the picture looks like this. The dark blue oval is the original graph, and now I add this S prime and edge of weight 0 from S prime to everyone. Okay, and now I will define also G1, which is pretty much like G0, except that I add 1 to every edge in the original graph, but not the edge from S prime, by the way. So it looks like this picture over here. And the goal is that I want to compute phi such that W plus 1, this graph G plus 1, is at least 0 everywhere. So this graph here, I want to make everything non-negative. And if I manage to do that, then I can conclude that W phi, again, without plus 1 now, W phi is at least -1, because to go from G plus 1 to the original graph, I just have to remove this plus 1 here, right? So it might cause some zero weight edges to be -1 instead, but that's the only thing that it can cause, okay? So again, the goal is to work with G plus 1 and to make sure that I have a good price function for G plus 1. Any question about this? So you might ask right now, why G plus 1? And by the way, you might realize that by adding plus 1 to every edge here, it might change the shortest path, right? So that is something you have to be careful too. But why G plus 1? So let me try to give you a brief idea. Basically, it allows us to connect something about the diameter of the graph with shortest path, okay? So I claim the following. But this is a warm-up lemma, by the way. This is not exactly what we use, but it's a good it's good to get an idea from here. So I claim that if in the beginning already the graph G has low diameter at most d, okay, for some parameter d, then and by the way, it means that the distance between every pair is at most d, right, small d. And I assume that there's no negative cycle in G as well. Then in the graph G plus 1, every shortest path has at most d plus 1 edges. So I can translate the diameter of the original graph to the number of edges in the shortest path in the graph G plus 1. Okay, this is kind of the relationship we're trying to make. So again, I have a graph here in this picture, diameter at most d. Now, if I add this dummy node, right, I create a graph and I add weight 1 everywhere, then I have G plus 1. I claim that the shortest path from S prime to every vertex V is at most d, contains at most d plus 1 edges. All right. So now the proof. So let's assume that this is not the case. So let's assume that the shortest S prime V path P in graph G plus 1 contains strictly greater than D plus 1 edges. So let's look at this picture here. From S prime, you have a path here that has the +1 edges. So now I define P prime to be just the original path P, but I forget about S prime. So P prime is this green subpath here. Okay, and I know that P prime has strictly has greater than D edges, right? Because I assume that P has strict greater than D +1 edges. And also another thing that I would like to claim is that the weight in the graph +1, so the weight +1 of P prime, so the weight here of the graph G +1 is at most 0. And that is because this is the shortest path, right? And I also have an edge of weight 0 from S prime to V. So the whole thing here has to be smaller than going directly from S prime to V, which is 0. So the whole part here is at most 0, and the green part is at most 0. So now W +1 of P prime is at most 0. Now I go back to the graph G. I claim that the weight of the path P in the graph G has weight at most strictly less than -D. And again, it's because to go from G +1 to G, I just have to remove this +1 from every edge. And that reduces the weight of the whole path by more than -D, because I have more than -D edges. Sorry, more than D edges. Okay. And now the last thing that I claim is that since I assume that the graph has low diameter at most D, so there must be a path from V to U of weight at most D in the last picture over here. So now if you look at the third and the number 3 and number 4 together, I can go from U to V with weight -D and then can go back with weight D. So the whole thing together is a cycle of weight at least -1, which means that this is a negative weight cycle. Okay, so 3 + 4 implies we have negative weight cycle, which contradicts the assumption that we don't have negative weight cycle in G. Okay, so this is pretty much the main idea. And I believe that once you understand this idea, this proof, you probably can start reconstructing the algorithm now. But now let me just spend the remaining 10, 15 minutes explaining to you a bit more about this. But let me now make it clear what's going to happen next. So I will have 3 graphs that I have to consider. G +0, which is again just the original graph plus some weights of edge of weight 0, and G +1, which means that I add 1 to every edge weight inside the original graph, and G +2, which is again I add 2 to every edge inside the original graph. Okay, and most of the action will be with G +1. So in the algorithm, you will see a lot of notation G +1, G +0, but I want to make it clear that G +1 is where things happen. G +0 will be used only for analysis. It will not appear in the algorithm at all. And G +2 will be used only once. And that's because of this property that G +2 has weight at least 0, right? Because I start with the graph where every edge has weight at least -2. Okay. And because of this, I can run low diameter decomposition on G +2. Okay? So this is the only place we use G +2, low diameter decomposition. And now G +1, what is happening? I will come up with a bunch of price function. So I will have 3 types of edges, green, blue, and red. You will see later what they are. But basically, I will come up with the first price function where I make the green edges non-zero. Okay, and then I will come up with from this graph G +1 phi 1, I will have another price function phi 2 that makes green and blue non-negative. And finally, I will have phi 3, which makes green, blue, and red non-negative, which means everything is non-negative now. And once everything is non-negative, then I know that, again, W phi +1 is at least 0, which means that W phi without +1 is at least -1. So that's the whole plan. Any question? Okay. If not, then I will now just explain the algorithm. And this is a warm-up algorithm which has running time of m root m. So the algorithm looks like this. So in the initial step, step 0, I will compute EREM, which is pretty much I run low diameter decomposition on G+2. And again, because G+2 has non-negative weights, it's fine to run LDD here. With parameter D equals root n, you will see later why D is root n. And now we will have strongly connected components in G+2 minus EREM. I will denote that by V1, V2, and so on. And I will also denote let EDAG to be the edges between these strongly connected components. And I use EDAG because it should form something that that looks like a DAG, a directed acyclic graph. In this graph, G2 minus EREM. Okay, so now the remaining will be about G+1. So first I will compute phi 1, which is by computing shortest path from S prime, the dummy source, to G+1, but I remove EREM and remove EDAG. If you look at the picture, it looks like this. So originally in step 0, I have a graph and I compute EREM, which is the red edges here. Okay. And now I compute strongly connected component of the graph when I remove these red edges. So I will end up with this green ovals and the blue edges that points only downward, only in one direction, which is called EDAG. And inside the SCC is the edges in SCC. And I know that each SCC has big O of D, weak diameter. Okay. And now I look at the graph where I remove the red and the blue edges. So I end up with this graph. And I compute the shortest path from S prime to every vertex here. I let phi 1 be the distance that I get. And I know that by that phi 1, every green edge will have non-negative weight because again, distance and distance give you a good price function. This is one fact that we know from the beginning. Okay, I haven't told you yet how I compute this shortest path, but just to give a hint, it's pretty much Bellman-Ford. Now in the second step, I will run fixed DAG edges on this graph that I have here with non-negative weights here, right? So now I add back the blue edges. They might be negative, but now I know that they go only in one direction. So I can run fixed DAG edges on this graph to come up with another price function that makes the blue edges non-negative and keep the green edges inside the SCC also non-negative. And in the last step, I will add the red edges back and they might be negative again. I know now that the blue and the green are non-negative, right? But the red might be negative. And now again, I have to compute a single source shortest path from S prime. And since this is a single source shortest path for the whole graph, I know that I will have a good price function. So I will eventually get phi such that W+1 phi is at least 0, which means again that I end up with what I want, right? Output W phi plus 1 is at least 0. And again, I haven't told you how this works, but it's pretty much Dijkstra plus Bellman-Ford for the last step. And now I return phi 3 as my price function. Okay. So I hope that it's clear that the algorithm produced the correct result because eventually in step 3, I compute shortest path in the whole graph. And I just return that distance as my price function. The only thing that is not clear is how much time it needs. But before that, any question? No question? All right. So now time complexity. So maybe let me skip the executive summary for the interest of time, and let me just go to each step one by one. So step 0, that is pretty simple. You just have to run LDD, and that takes near linear time. And in step 2, that is also simple because we have already discussed fixed DAG edges. So the key things are in step 1 and step 3. We have to analyze the running time of these two steps. So for step one, you don't see my slide anymore, right?
In anymore. Yeah.
1 second, I think it breaks. So can you see the whole thing in one screen?
Yes.
Yes, great. So yes. So right, step one, runtime. So, and this step is pretty much the same as what we have seen before. So let me claim one theorem first. The theorem is the path P, which is if I define P to be any shortest path from S prime to V for any vertex V for now, this shortest path in the graph G plus 1 minus E rem minus E dac, which means just look like this. I forget about the red and the blue edges. Then P contains at most D plus 1 edges. So why is that the case? So again, this is the shortest path, right? And I claim that the whole thing here contains at most D plus 1 edges. And the proof is pretty much the same as what we have seen before. So I'm going to go through this a bit quicker. So again, the claim is that the shortest path here contains at most D plus 1 edges, right? So suppose it contains more than D plus 1 edges, where D is the parameter of low diameter decomposition. So now I look at the subgraph, subpath from U to V inside the SCC, right? So I know that it has strictly greater than D edges. And I know that the weight of this path, P prime, between U and V, is at most 0 because, again, from S prime, I can go directly to V with this edge, blue edge of weight 0. Okay? So now this is the graph G plus 1 minus E minus E dac. Now, if I go back to G, then I have to remove this plus 1, which means that the weight of the path P prime will be strictly less than minus D. Okay? And now I also know from low diameter decomposition that from V to U, there is a path in the graph G of weight at most D. So now again, I have a negative cycle by step 3 and 4 together. Okay. And again, the only step 4 is where I need low diameter decomposition, right? So that I know that the distance from V to U is small. So now I have this theorem that says that every path contains at most D plus 1 edges. Then I'm pretty much done. I claim that if every path contains big O of D edges, then I can solve single source shortest path in MD time. Okay, and this is because you just have to modify Bellman-Ford algorithm. Bellman-Ford algorithm usually run a for loop for n time, but it's a simple exercise which you can find in textbook that if the number of negative, if the path contains at most D edges, then you just need to run the for loop D times instead. So now the last thing that I need to do is step 3. So I claim the following. So let me now define a few more things. And yes, I'm sorry that I might be 5-10 minutes late, by the way. So I define eta phi 2 of V to be just the number of negative edges. So right now I'm at step 3, right? So I have phi 2 here. The graph is G plus 1 phi 2. And now I'm interested in the shortest path from S prime to V in the graph G plus 1, and which is the same as G plus 1 phi 2, this graph that we have right now. Again, it's the same shortest path because phi 2 doesn't change, price function doesn't change shortest path. And now I define eta phi 2 V to be just the number of negative weights inside this graph, G plus 1 phi 2. So its edges in this shortest path with weight at least strictly less than 0. Okay, and my theorem is that expected number in expectation phi eta phi 2, and the randomness is on phi 2, right? Because to get phi 2, I need to compute LDD, and that LDD is a randomized algorithm. It's based on EREM. So this but in any case, this expectation is big O of n divided by d. Okay, meaning that the shortest path between G plus 1, phi 2 contains n over d negative edges in the expectation. So why is that the case? And so to prove this, actually, we just have to prove that the shortest path doesn't contain many edges in EREM, right? Because in the last step here, I have already made the green and the blue edges non-negative, and the only negative edges here is red edges, which are the EREM edges in EREM. Yes. So now I'm going to prove that the path expect the number of edges in EREM that is also in PS prime V is big O of n divided by d. And again, this is sufficient because only edges in EREM can be negative in this graph. So recall that we call LDD G plus 2D. And we know that the probability that an edge is in EREM is roughly W plus 2 divided by D. So now we just have to analyze what is W plus 2E and W plus 2 of the whole path. So recall that since we define PS prime V to be a shortest path in G plus 1, we know that the weight in the original graph, W plus 1, is at most 0 because, again, we have this edge of weight 0 here from S prime to V. And now the weight of this part in W plus 2 is at most n because we will just have to add 1 on every edge in this part, right? And there are at most n edges. So we know now that W plus 2 is at most n. So now the expectation, this expectation that we want to compute is roughly the weight of the path divided by d by union bound, which is n here divided by d. And that's it. Any question about this proof? And again, the whole idea is to use the property that an edge is added to EREM with small probability.
Hey,
So now, yes.
So you like the choice of d as square root n was to balance these two, like it's md
Exactly.
times. Okay.
Yeah. Exactly. MDs and n over d. Exactly.
Okay.
Yes. So now, once we know this, I claim that we can solve single shortest path in the time that is proportional to this number of negative edges in the graph. And in particular, I claim that we can solve the problem in the sum of V eta of V. Okay, this claim need the assumption that I have big O of 1 max degree, by the way. So suppose this claim is true for now, I will come back to this. Then we have a corollary that in step 3, we only need n squared divided by d because, again, eta of V is n in expectation. So when you sum everything together by linearity of expectation, is just n, you sum over n of them, right? So it's n squared divided by d. So now let me give you a quick idea of claim 2. So, and it's pretty much just an algorithm that is a combination of Bell-Manford and Dijkstra. So instead of giving you the full version, let me give you a warm-up version first, where I assume that for every V, eta V is at most k. Okay, so the sum of eta V is nk, but I'm assuming something stronger than this, that eta V is at most k for every node V. I claim that then in nk time, I can compute the shortest path. And the idea is roughly this. We will just use Bell-Manford and Dijkstra algorithm for k rounds. Alternatively, the pseudocode is on the right. Pretty much the black stuff are from the textbook, are the normal Dijkstra and Bell-Manford, and you just have to add this repeat until over here, and that's it. You just have to run Dijkstra and run Bell-Manford alternatively. And the key idea is, if you look at the picture on the left, if I have, let's say, shortest path 3, where the green edges are non-negative and the red are positive, right? When I run Dijkstra algorithm once, I should get everything correct up to the first, green part here. And when I run Bell-Manford once, I should get everything correct up to here, to the red, to the first red. And the next Dijkstra will get you correct distance up to here. The next Bell-Manford will get you correct up to here. and so on. So if you have only k red edges from S to any part here, meaning k negative edges, then k rounds of this Dijkstra and Bellman-Ford should compute the distance correctly. So this is a concrete example. Dijkstra get you correct up to here. This is your shortest path 3. And then Bellman-Ford get you from A to B, and then Dijkstra gives you the rest, right? So this works if eta v is bounded for every v. But now if eta v is not bounded, then we have to do a bit more. And the key idea is something called laziness, where you will allow the node to participate in the computation only when it's really necessary. And here is pretty much the pseudocode. I need to modify it a bit more here. Basically, I need to define the queue, which you already need, right? But I have to do it a bit differently. And I will add a vertex to, I will run something called relax here, only for some vertex. So I have some condition here. So it's very small modification. And the key idea is this. Suppose you have this kind of graph, right? That the negative are at the very end and the positive are here. Then if you run just Dijkstra and Bellman-Ford every time, then the edges in the green, the vertices, the green part, will always participate in computation. But you know that it's not necessary. If you run Dijkstra here up to here, and then you run Bellman-Ford, then these vertices here shouldn't participate in the computation in the future. So you just have to keep running Bellman-Ford, and the nodes that should participate in the computation is just here. Okay, so in the end, the nodes should participate in the computation only either time when its distance change. When its distance kind of stable, then it stops participating in the computation. So this is the claim. After iteration, you will get correct distance SV if eta v is at most I. So V will contribute either time in total. That's the rough idea. And to summarize, the first step takes md time, and the last step takes n squared over d time. So in total, you have m root n roughly time when you set d to be root n. So now how can you get near linear time? I only need one more idea. So I need to recursive. So instead of setting d to be root n, now I need to track some parameter called delta here, which is the number of edges in any shortest path in the graph g plus 1. And when I call scale down, I will call it with parameter d plus 1 as before, but I will just use delta to be just d to be delta over 2. And so now I call the same algorithm here. I recurse here. I don't solve shortest path using Bellman-Ford anymore. This is a recursion. And in the last step now, by the theorem that we have seen before, the expectation of eta is delta divided by d. You can just, rework the whole proof and get delta divided by the parameter. And now delta divided by d is just 2. So now the whole thing is just the time that you need for the last step is just on. Okay, so the last step now takes on, and the first step, you don't know what time, but you recurse. And then you just need to recurse log n times because every time delta decreased by a factor of 2 roughly. So that's the main idea. And of course, here I look at the special case where I have number 2 and number 1 here, but you can make it 2b and 1b, and you just replace 1 and 2 by b everywhere. And that's pretty much the whole algorithm. So this is the whole algorithm. So let me now jump to the conclusion, unless you have any question right now. So to summarize, we have a near linear time negative single source shortest path algorithm, and I think the only key idea that is important is low diameter decomposition. And let me end with some open problems. For single source shortest path, I think the very exciting problem is, can we get strongly polynomial time that is better than Bellman-Ford, which is OM, meaning that we don't want to have anything like log W. And how about other settings? Distributed parallel and streaming algorithm can we be as fast as non-negative case for these settings. And for a broader problems, do we have some different algorithms for problems that are solvable by mean cost flow? since this is a powerful tool now that solve a lot of problems. But hopefully we would like to have an algorithm that may be simpler, more that's something that is implementable, experimentable, teachable, right? And something that works across different models of computation. And also beyond mean cost flow, we also have problems that we don't know how to solve yet. Just to give you a few examples, non-negative bipartite matching, directed cuts, vertex cut. We don't know near linear time algorithm yet. And I think now that we have mean cost flow as a powerful tool, maybe we can use it, or maybe we need something completely different. So this concludes my talk. Thank you very much.
Thanks so much for your talk, Danupon. I have a feeling this result might make its way into textbooks in the near future. We'll take any questions from the audience. No? So I also had a question in one of your slides. In fact, just prior to specifying steps 1 to 4, we had mentioned that there are connected SCCs which have diameter weak diameter D. So is there a step before this where we identify these SCCs of diameter at most D by removing certain edges, or does that take time at all? Or did I miss something?
Sorry, you mean this step 0 to 3, right? Here?
Yes.
And you would like to identify SCC of small diameter? Is that what you mean?
Yes, yes, yes. How much? So it does take some sort of running time as well.
So you it's just guarantee from low diameter decomposition that if you just compute the SCC of this graph, G plus 2 minus EREM, then every SCC will have low weak diameter. So you don't need to check that. You can just, take that as a fact that once you compute SCC, then it will have low weak diameter automatically. Okay.
Okay.
The algorithm of course has low probability of being incorrect, right? But you just check in the very end. You know that if it's correct, then the running time of each step should be something. And so if that doesn't happen, then you know that something goes wrong, and that's where you can report that something went wrong, and that's why it can be Las Vegas.
So, a quick question, Danupon. So,
Yes.
are there other savings that you can foresee if I want some approximation guarantees? I'm wondering.
Oh, approximation.
So, yeah,
You mean in saving in terms of logs, right? Or
yeah, some so yeah, even
so,
better
but
running
that's
times.
I see. That's a very good question. From my experience, I work on approximate shortest path too, and at least from my experience, when you talk about directed graph and with negative weights, approximation doesn't really help reducing the resource. But it's just,
it could be
from
exactly
experience.
0 and then any multiplicator.
Yes, exactly. Yes.
Okay. So the other one is slightly maybe a tangent, but the way I appreciate these low diameter decompositions is as you mentioned, it has these initial connections to the work of Berthal and all these embeddability of things. So it does, and so there are even stronger decomposition results for graphs with structures or for metrics with structures. So do you think those are interesting directions as well? Let me ask it in a slightly more technical manner. What are the if I look at the statement of load LDD that you mentioned right up front, what strengthenings can I do to actually then translate that into a faster running time?
I'm sorry, can you rephrase the algorithm once more? I'm sorry.
No, I'm just saying, let's say I give you some a strengthening of LDD. So I tell you that here's a graph, and for this, I can, let's say, improve upon the probability bound that you remove an edge, or
Right.
it's almost an LDD to begin with. Does that give you some savings in the? I'm just trying to understand, like, how does that, like, are there structures on the graph that I can assume, which would then give me even like a further improvement?
Advantage.
Yeah.
Right. Yes. I guess
Like
as you mentioned.
Principal-Rao
Yes.
example, like for planar
Right.
graphs is already known, but I'm wondering if one can recover that result using the fact that like LDD for planar graphs is better.
Okay, I see. To be honest, I haven't thought about this question. This is a very good question again. So, and to be honest, again, all of us, meaning Aaron and I and Christian, who wrote this paper, we are not expert in LDD. We kind of, this is the pretty much, the first time we kind of developed LDD, including the previous paper, right? Yeah, so we are not sure, but it might be possible, and yes, that might be something interesting to do, right? To try to recover everything else, or even get stronger results using LDD decomposition. Yes, but it has to be very different from what we use, because we really, the way we connect LDD decomposition to shortest path is via this weight scaling, right? Like change the most negative from -1 to 1, and that will give you log mu. But this Factor-Renpon and Rao's result on planar graph, that doesn't have log mu. So we yes.
Okay. Yeah.
But yeah, that's very interesting.
Yeah, I'm just curious because like for those, like for planar graphs or for like planar metrics, you do have better decomposition results, like even
right.
for
right.
yeah. So
right.
just curious because of that.
Yes, and I think directed load LDD, this is very new. So I think developing this for like everywhere, that I think that is very important, very interesting anyway on its own.
Okay. Thanks.
Thank you.
So I had a question. So this sort of algorithm and the analysis you did crucially requires the weights to be integral. So do you think there might be any modification that or an approach that might extend this to non-integral weights?
Yes, that's yes, and yes, that's a very exciting direction, which I really have no idea, because yes, beating OMN, right, of Bell-Manford, I don't see at all how this approach right now will give you anything even slightly better than OMN. So yeah, my answer is that I don't see how to do that.
Okay.
Thanks.
Okay, if there's no more questions, I'll stop the recording now, and maybe a few of us, if we are, we can stay back and just have a more informal conversation. Thanks so much for joining us.
Thank you for joining.